Welcome to the deep dive. Today, we're going to be looking at centered hydrocarbons.
Ew, fun.
These are molecules with a central carbon atom that's bonded to 4 other carbon atoms.
Yeah.
And we're going to start this journey with a sequence from the OEIS. That's the Online Encyclopedia of Integer Sequences.
Right.
And this is a website that's a treasure trove for any math enthusiast.
I love it.
The sequence we're looking at today is A0000022.
Okay.
And this sequence counts the number of possible centered hydrocarbons you can actually make with a given number of atoms.
So what's interesting is this sequence actually has a connection back in history.
Oh, really?
Yeah, all the way back to the 1870s with a mathematician named A. Cayley.
Okay.
And he was really doing some pioneering work in using math to understand chemical structures.
Wow, that's amazing how these sequences can have such a historical connection.
Yeah.
Now, when I look at this sequence, the first few numbers are 010112.
Right.
Can you maybe just explain what these numbers actually represent?
Yeah, so you can think of this sequence as starting at position 0.
Okay.
Which represents 0 atoms.
Okay.
So if you look at the one at position 4, that means there's only one possible centered hydrocarbon you can build with 4 atoms.
Got it.
And that's methane.
Ah, methane.
Yep.
The simplest of the molecules.
Exactly.
But I also noticed that there are some zeros in the sequence.
Yeah.
Can you explain why there are zeros?
Yeah, that's a great question, and it kind of highlights how we're dealing with real-world limitations in chemistry.
Oh, okay.
If you only have 1 or 2 atoms,
Right.
you just can't make a molecule that has a central carbon atom linked to 4 others.
Yeah, that makes sense.
So those zeros represent these structural constraints.
So it's like the sequence is telling us all the theoretical possibilities.
Yeah.
But then the zeros are bringing us back down to earth.
Exactly.
Reminding us that chemistry has rules.
Right.
There are constraints.
Yeah. And even A. Cayley, as brilliant as he was, when
Yeah.
he was first calculating these numbers, he actually made some errors.
Oh, really? Because he didn't fully account for all the constraints of chemical bonding. One of his contributions, though,
Yeah.
was the idea of using trees from graph theory to represent these hydrocarbon structures.
Hold on, trees.
Yeah.
Like the ones in a forest?
It might sound strange, but in math, we have these things called trees.
Okay.
Specifically in graph theory, and it's a way to represent connections visually.
Okay.
So imagine each carbon atom as like a dot,
Okay.
and then the bonds between them are lines connecting those dots.
Okay, I'm visualizing it.
And the way these dots and lines are arranged can create these branching structures that look like trees.
Oh, okay.
So Cayley realized he could use these trees to represent and categorize different types of hydrocarbon structures.
So instead of leaves and branches, we have atoms and bonds.
Exactly.
That's a very cool way to visualize it.
Yeah.
But why does knowing how many centered hydrocarbons are possible even matter?
Right.
What's the practical use of knowing this information?
That's where it gets really interesting.
This actually has significant implications in fields like drug discovery.
Okay.
So let's say scientists are trying to design a new medication.
Right.
Understanding these possible structures of these hydrocarbons helps them create targeted molecules that can fit specific receptors in the body.
So it's like having a blueprint to build a molecule for a very specific purpose.
Exactly.
Where?
And it goes even beyond medicine, too.
Okay.
This is valuable in material science. Researchers are always looking for new materials with unique properties.
Right.
And understanding how centered hydrocarbons are structured can help them create those materials.
Wow, the applications are wider than I imagined.
Yeah.
I'm starting to see how a seemingly abstract mathematical sequence can have a real-world impact.
It really can.
It's pretty cool.
And there's even more.
Okay, what else?
It can help us understand the vast diversity of organic molecules in space.
Oh, wow.
So astronomers will use this information when they're analyzing data from telescopes and probes. And it can help them identify and understand the complex molecules that exist beyond our planet.
Wow, this is incredible.
Yeah.
It's like this one sequence connects us to everything.
Right.
From the medicine we take to the stars above.
It really does.
Okay, let's look at some specific examples from the sequence.
Sure.
How many centered hydrocarbons are possible with 12 atoms?
With 12 atoms, that number jumps to 86.
Wow.
You can start to see how quickly the possibilities expand as you add more atoms.
86 different ways to arrange those atoms.
Yeah.
What about if we go even bigger?
Okay.
Say 30 atoms.
With 30 atoms, get ready for this.
Okay.
The number skyrockets to a whopping 74,883.
74,883.
It's really a testament to the amazing complexity that arises from just a few simple rules of chemical bonding.
74,883. That's like a vast universe of molecular possibilities just waiting to be explored.
Exactly.
This OEIS entry, I have to say, it's like a rabbit hole.
Oh, yeah.
It's not just the sequence itself,
Right.
but it's all the links to research papers and algorithms.
Right.
Yeah. Even like visual representations.
And that's the beauty of the OEIS.
Yeah.
It's like a springboard for further exploration.
Yeah.
A gateway to deeper understanding of the relationship between mathematics and the physical world.
So for our listener today,
Yeah.
we've gone from a seemingly simple sequence of numbers to uncovering a world of chemical complexity and mathematical intrigue.
It is pretty fascinating.
But we've only just scratched the surface.
We have.
There's so much more to uncover.
There is.
And the OEIS is a perfect tool for that.
But before we dive deeper, let's actually take a closer look at some of those different structures that can come from these centered hydrocarbons.
Okay.
Remember we were talking about trees earlier?
There's branching structures.
Right.
Representing atoms and bonds. I'm curious to know more.
Well, imagine that you're building these molecules with like a molecular modeling kit.
Okay.
So you have your central carbon atom, and then you start attaching those 4 other carbon atoms. But there's so many different ways that you can attach them.
Oh, really?
You can create straight chains.
Okay.
You can have rings forming.
Yep.
You can even have branches upon branches.
Wow.
Creating these really intricate shapes.
So it's kind of like building with Legos.
Yeah.
You start with the same basic brick.
Right.
But you can end up with a castle or a spaceship.
Exactly.
Or even a giant robot.
Yeah.
Depending on how you put them together.
That's a great analogy.
And I'm guessing this structural diversity is what makes centered hydrocarbons so important in the fields you mentioned earlier.
Yeah.
Like drug discovery and material science.
Absolutely.
Yeah.
Because the shape of a molecule determines its properties.
Makes sense.
So for instance, in pharmaceuticals, even just a slight change in the structure of a drug molecule can dramatically alter its effectiveness or side effects.
Wow, so it's not just the number of atoms? It's how they're arranged in three-dimensional space.
It is.
It's like a molecular dance.
Oh, yeah.
And each unique move is creating a different effect.
Precisely.
I love that analogy.
And this is where Cayley's work becomes even more fascinating.
Okay.
Because he was one of the first mathematicians to try and systematically categorize these different structural arrangements. Using that concept of trees in graph theory, he realized you could use these trees to represent and count the different possible isomers of hydrocarbons.
Isomers, now there's another word.
Yeah.
I'm intrigued.
So isomers are molecules that have the same chemical formula, but different structural arrangements.
Okay.
So for example, imagine you have 6 carbon atoms and 14 hydrogen atoms.
Right.
You could arrange those atoms in multiple ways to create different molecules, each with its own unique properties.
So it's like having the same ingredients, but making a cake versus a pie.
Exactly.
Same stuff, different outcome.
That's a perfect analogy.
I like that.
And Cayley's work laid the foundation for understanding this structural diversity in hydrocarbons.
Right.
Which is so crucial in fields like chemistry, biology, and material science.
I am really starting to appreciate how this seemingly simple sequence of numbers unlocks this whole world of chemical complexity.
It does.
It's amazing how something as abstract as a mathematical sequence can have such profound real-world implications.
And that's just the beginning.
What?
There's so much more to explore within the OEIS entry.
Oh, really?
And in all the research that it connects to.
Wow, you're right. This deep dive has been a real eye-opener.
Yeah.
And we've only just scratched the surface of the vast information that's available in the OEIS.
Yeah, before we wrap up, though,
Okay.
I do want to emphasize one more thing.
Okay.
The OEIS is an incredible tool.
Yeah.
But it's just a starting point.
Okay.
The real magic happens when you, the listener, take that information and run with it.
You mean don't just passively absorb the knowledge?
Right.
Go out and do something with it?
Exactly. Don't just be a spectator.
Yeah.
Be an explorer.
Okay.
Be a discoverer.
Oh.
Dive into those links in the OEIS entry.
Yeah.
Read the research papers.
Okay.
Maybe even try to write your own algorithm to generate the sequence.
Oh, wow.
The more you engage with the material, the more you get out of it.
So it's a call to action.
It is.
Don't just learn about it.
Right.
Actively engage with it.
Exactly. The OEIS is this collaborative effort.
Yeah.
It's a constantly evolving database.
That's pretty cool.
That thrives on the contributions of curious minds from all over the world.
I love that.
Who knows? Maybe you'll be the one to uncover a new pattern.
Wow.
A new connection.
Yeah.
A new insight that even the experts haven't thought of yet.
That's an exciting thought.
It is.
So for our listener out there,
yeah,
we challenge you to be more than just a recipient of information.
Right.
Be an active participant in the world of mathematical knowledge.
You got it.
And who knows, your journey might just start with this humble sequence.
Yeah.
0000002 and lead you to uncharted territories of scientific discovery.
Absolutely.
That's a great note to end on.
It is.
But before we send our listener off on their own adventures,
okay,
there's one final point I think is worth emphasizing.
All right, let's do it. Yeah, it really is a vast world. But let's not get ahead of ourselves. We were just talking about how those numbers in the sequence represent different structures.
Right.
Like it's not just about the quantity.
Yeah.
It's about the diversity of those structures.
That's right. We were comparing it to building with Legos, remember?
Exactly. You can have straight chains of carbon atoms branching out from that central carbon. You can have rings forming. You can even have branches upon branches creating these really intricate shapes.
So it's not just a simple line of atoms. It gets much more complex than that.
Much more complex. And you might be wondering, why does this structural diversity matter?
Well, think about it this way. The shape of a molecule is crucial because it determines how that molecule interacts with other molecules. Okay, that makes sense. The shape dictates how things fit together, like a key fitting into a lock.
Precisely. And this has huge implications in various fields. For instance, in drug development. Scientists are trying to design medications that interact with specific targets in the body.
Right.
And the shape of the drug molecule is critical because it needs to fit perfectly into that target like a puzzle piece.
So understanding the different possible structures of centered hydrocarbons helps scientists design drugs that are more effective and have fewer side effects because they fit their targets more precisely.
Exactly. It's like tailoring a suit. You want it to fit just right. And this knowledge isn't just limited to medicine, it's also crucial in material science.
How so?
Well, researchers are always on the lookout for new materials with unique properties like strength flexibility or conductivity.
Right.
And by understanding how the structure of centered hydrocarbons influences their properties, scientists can use that knowledge to design and create new materials with specific characteristics.
So by manipulating the arrangement of those atoms, they can fine-tune the properties of the material.
It's like having a molecular toolkit, and understanding these structures gives you the instructions on how to use the tools to build what you need.
That's incredible. And this brings us back to Cayley and his work with trees in graph theory. How did his work contribute to our understanding of this structural diversity?
Cayley's work was groundbreaking because he realized that you could use those trees to visually represent and categorize the different isomers of hydrocarbons. Remember, isomers are molecules that have the same chemical formula but different structural arrangements.
Right, like the cake versus pie analogy. So Cayley's trees provided a way to visualize and differentiate between these different isomers.
Exactly. It was a huge step forward in understanding the complexity of these molecules, and that understanding, as we've been discussing, has paved the way for advancements in so many fields.
It's truly remarkable how a seemingly simple concept, a central carbon atom with 4 bonds, can lead to such a vast and diverse world of molecular structures.
It is, and that's the beauty of science. Often the most fundamental concepts lead to the most profound discoveries and innovations.
Well said. This deep dive has been a real eye-opener, and we've only just scratched the surface of the vast information available in the OEIS.
I agree, but before we wrap up, I want to emphasize one more thing. The OEIS is an incredible tool.
Yeah.
But it's just a starting point. The real magic happens when you, the listener, take that information and run with it.
You mean don't just passively absorb the knowledge?
No.
Go out and do something with it.
Exactly. Don't just be a spectator, be it an explorer, a discoverer. Dive into those links in the OEIS entry, read the research papers, maybe even try to write your own algorithm to generate the sequence.
It's a call to action. Don't just learn about it, actively engage with it.
You got it. The OEIS is a collaborative effort, a constantly evolving database that thrives on the contributions of curious minds from all over the world. Who knows, maybe you'll be the one to uncover a new pattern, a new connection, a new insight that even the experts haven't thought of yet.
That's an exciting thought. So for our listener out there, we challenge you to be more than just a recipient of information. Be an active participant in the world of mathematical knowledge.
And who knows, your journey might just start with this humble sequence, A00022, and lead you to uncharted territories of scientific discovery.
That's a great note to end on. But before we send our listener off on their own adventures, There's one final point I think is worth emphasizing.
Yeah.
Yeah, you're right. There is one more thing. We've talked about how fascinating the sequence is and how it connects to real-world applications.
Mhm.
But there's also a certain beauty to it, wouldn't you say?
Absolutely. This sequence in its simplicity, I think, reveals a profound truth about the world.
Okay.
It shows us that even in the midst of this immense complexity,
Yeah.
there's this underlying order, a predictability that can be expressed mathematically.
It's like the universe is speaking to us through these numbers, whispering its secrets in a language we can begin to understand.
That's a beautiful way to put it. And what's
Yeah.
even more remarkable is that this sequence,
Yeah.
it's just one tiny piece of this vast puzzle.
Right.
The OEIS is full of countless other sequences,
Yeah.
each with its own story to tell,
Wow.
each offering a glimpse into the intricate patterns that shape our world.
It is a bit overwhelming, isn't it?
Yeah.
To think about all those sequences out there waiting to be explored, waiting to reveal their secrets.
It is, but it's also incredibly exciting.
Yeah.
It reminds us that there's always more to learn, more to discover.
Right.
And that sense of wonder,
Yeah.
that drive to explore the unknown,
Yeah.
that's what makes this journey so rewarding.
You've given our listener a lot to ponder today. We've journeyed from the basic structure of a centered hydrocarbon molecule to the vastness of the cosmos, all thanks to a single sequence of numbers.
And that's just the beginning. Who knows where your own exploration of the OEIS will take you? Maybe you'll find a new connection, a new application, a new insight that no one has ever seen before.
That's the beauty of it, isn't it? The possibilities are endless. So to our listener, we encourage you to dive in, explore, and see what wonders you can uncover.
It's been a pleasure sharing this deep dive with you. Remember, the journey of discovery never truly ends.
Thanks for joining us on the Deep Dive. Happy exploring.